Welcome back to the deep dive. It is so good to have you here with us. I want to start today by asking you to just take a second and look around the room you're sitting in right now.
Mm,
Maybe you're driving in your car, maybe you're cooking in your kitchen, maybe you're out for a run. Wherever you are, there is a force operating right now all around you, penetrating the walls, penetrating your body that is, well, it's effectively magic.
it really is. It's
Yeah.
the very definition of action at a distance.
Right. We treat it as so mundane. We use it to stick a grocery list to a refrigerator door or to keep a cabinet closed. But when you actually stop and peel back the layers, it is one of the most baffling, complex, and absolutely essential forces in the universe.
It's an invisible hand that can push and pull objects without ever physically touching them. And you're right, we do trivialize it with fridge magnets, but we are talking about a force that literally shields the entire biosphere of Earth from extinction-level radiation.
That is a wild escalation from fridge magnets to planetary shields, but that's exactly why we are here.
It creates a shield that protects the Earth, and it also, and this is the amazing part, it also acts as a recorder. It writes a hidden history in the rocks at the bottom of the ocean that tells us how our planet was formed.
It's a force that has guided explorers across uncharted oceans, baffled ancient scientists for centuries, and is now, well, it's fundamental to almost every single piece of modern technology we own. Today, we are grappling with Chapter 16, magnetism.
A classic topic,
Yeah.
and one that's full of surprises.
We are pulling this primarily from the Cambridge IGCSE physics curriculum, specifically the third edition, but we're also layering in some supporting materials from Oxford AQA and Pearson to get the full high-definition picture. Now, I know what some of you might be thinking. Physics class, year 10, bar magnets and iron filings. I know this.
Right. Been there, done that. And while the source material is a physics textbook, which, might sound a little dry,
Don't let the word textbook fool you. The mission for this deep dive isn't just to help you pass an exam or to memorize which poles attract or repel. That's the easy part.
that's the surface level.
We want to understand the underlying physical rules that govern everything from a tiny compass needle to a massive scrapyard crane.
And we want to connect the dots. We wanted to take those isolated facts you might remember, like opposites attract, and show how that simple rule actually shapes our understanding of the planet's history and its future.
Exactly. It's about seeing the invisible machinery of the universe. So let's unpack this. We need to start with the absolute basics, the fundamental rules found in Section 1. The text introduces us to the bar magnet.
The laboratory classic. It's usually a rectangular bar of steel, often painted red and blue, or sometimes just red and silver. It sits in the drawer of every physics classroom on Earth.
It really does. And it has these two distinct ends, the North Pole and the South Pole. Now, the text makes a really specific, almost you could say pedantic distinction here about these names right at the start. They aren't just North and South arbitrarily, are they? It's not like someone flipped a coin.
No, not at all. This is where the history of science really comes in. The full technical names are actually the north-seeking pole and the south-seeking pole.
Seeking. I like that word. It implies movement. It implies a goal and intention.
It does. It implies an active behavior. If you take a magnet and suspend it freely, say, you tie a string around the center and let it dangle so it can spin without any friction, one specific end will always, always swing around to point towards the Earth's geographic north.
It hunts for the North.
Exactly. That end is the north-seeking pole. The other end, naturally, points towards the geographic south, so it's the south-seeking pole.
But because physicists and people in general are, well, let's say efficient creatures who like to save time,
We drop the seeking. We just call it the North Pole and the South Pole. It's just easier to say. But remembering that seeking part is actually crucial
why so crucial?
because it's the key to understanding why compasses work. And it's absolutely essential for understanding the big confusion about the Earth's own magnetic field, which I promise we will get to later. It messes with everyone's head.
Okay, a little foreshadowing.
All right.
So we have these two poles, north and south, and this leads us to the first major law, the golden rule of magnetism, as I like to call it. It governs how they interact.
It's the rule everyone knows, even if they haven't taken a physics class in 20 years.
Mm.
Like, poles repel, unlike poles attract.
Opposites attract. It's a cliche in romance novels, it's a pop song, but in physics, it is a rigid, unbreakable law.
It is. And in the context of Chapter 16, this isn't just a casual observation. It's a measurable force.
Yeah.
If you bring a North Pole near another North Pole, you will feel a physical resistance, a push they do not want to touch.
And same for two south poles.
Same for two south poles. They repel just as strongly. But if you flip one around, you have a north facing a south.
Snap. They pull together.
Instantly.
Yeah.
Sometimes with a surprising amount of force.
I think we take this for granted because we play with magnets as kids. But stop and think about how weird that is. You aren't touching the other object, but you can feel it pushing back.
It is weird. It's a force field. It's as close to real-life telekinesis as we can get.
Okay, so the text mentions an activity here, activity 16.2, which I thought was really helpful because it gives us a way to visualize this. Because again, we can't see the magnetism itself. We need a model to help our brains process it.
Right. Physics relies so heavily on models to explain things we can't see with the naked eye. Things like atoms, or in this case, fields. The text suggests using an elastic band model to visualize the magnetic field lines.
Okay, walk me through this. Imagine invisible elastic bands connecting the magnets.
Exactly. So picture two magnets. You have a north pole on the left and a south pole on the right. Unlike poles, the model asks you to imagine there are invisible rubber bands stretched across the gap connecting them.
Okay, I'm picturing it. Stretched taut.
Right. And what does a stretched elastic band want to do?
It wants to shorten. It wants to snap back. It wants to pull the ends together.
Precisely. That represents the force of attraction. The magnetic field lines behave like stretched elastic, trying to shorten, pulling the magnets together until they collide. It gives a reason for the pull.
That makes total sense. It gives you a physical reason for the pull. But what about repulsion? Two north poles facing each other. You can't have elastic bands connecting them if they're actively pushing apart.
No, you can't. In the repulsion scenario, the model has to change. It asks you to imagine that the field lines coming out of the poles are like solid streams of jelly. Or better yet, like pressurized balloons being squeezed together.
Balloons? How so?
Think of the field lines as being squashed. They come out of the North Pole, they loop around. But when another North Pole gets close, the lines from each magnet push up against each other.
They're fighting for space.
Exactly. There's a lateral pressure, as the textbook calls it. The lines are being squashed together, pushing sideways against each other, trying to force the magnets apart so they have room to expand again.
And the text notes that the closer the lines are, the bigger the pressure.
Yes. That represents the strength of the field.
Yeah.
The closer you force those two repelling poles, the more you squash those imaginary lines, and the harder it becomes to push them any further. The invisible spring pushes back harder.
I really like that mental image. It moves it from just an abstract rule like repel to something I can almost feel in my hands, tension and pressure.
It's all about making the invisible tangible.
But let's talk about these lines a bit more. We keep saying field lines. We're moving into section 2 of our outline now, magnetic fields.
Mapping the invisible.
The text defines a magnetic field as the region around a magnet where a magnetic material experiences a force. That's a pretty standard definition. It's the zone of influence.
Right. If you're outside the club, you don't hear the music. If a magnetic object is outside the field, it doesn't feel the force. Simple as that.
But how do we actually know what shape this field takes? I mean, really know. We can't see it.
We have two main detective tools mentioned in the source material. The first is the messy, fun one that everyone remembers from school. Iron filings.
Oh, yeah. I remember this. You'd put a magnet under a piece of paper and you sprinkle these little iron shavings on top. It always made a huge mess.
It does, but it's so effective. You sprinkle them, and then, and this is the key part, you tap the paper gently.
Why the tap? I always wondered about that.
The filings have inertia, and they have friction against the paper. They don't want to move. The tap gives them a little jump, just for a millisecond, breaking that friction so the magnetic force can grab them and twist them into alignment.
And what happens? What do you see?
You see this beautiful, almost organic pattern emerge. These elegant, curved lines. Arcs that loop from one pole all the way around to the other. And crucially, they cluster.
They bunch up at the ends, right? At the poles.
Right. That visual clustering is data. It tells us that the magnetic field is strongest at the poles, because that's where the lines are most concentrated. The more lines you have in a given area, what we call the flux density, the stronger the force.
So the iron filings give us the intensity map and the general shape. But the text also mentions a second method, activity 16.1, which uses a plotting compass. Why bother with that if the iron filings work so well?
The iron filings have one major limitation. They show you the pattern, but they don't tell you the direction.
What do you mean?
Iron filings are just tiny slivers of metal. They don't have a north or a south head. They're just lines on a road without any arrows. They show you the highway, but they don't tell you which way the traffic is flowing.
Ah, okay, I see.
Exactly. To know the direction of the flow, you need a sensor that has polarity itself. You need a plotting compass.
A plotting compass is just a tiny magnet itself, right? In a little plastic case.
Yes, usually very small, maybe a centimeter across, so it doesn't distort the fields you're trying to measure. If you place it near a bar magnet, its own little needle will snap into alignment and point along the field line at that exact spot.
So the activity involves placing this compass right at one pole, seeing where the little arrow points, and making a dot on the paper.
And then you move the compass so its tail is on the dot you just made, see where it points next, and make another dot in front of its tip. You are literally tracing the path, dot by dot, step by step.
It sounds tedious.
It can be.
Hmm?
But when you connect all those dots, you get one of those perfect curved lines you saw with the filings. But now you can draw arrows on it. You know the direction.
And this leads to the convention, the universal rule of physics that we must follow. Magnetic field lines always act from north to south.
Always. By definition. The arrows on your diagram must point away from the North Pole and towards the South Pole.
Why that direction, though? Is it just an arbitrary choice somebody made?
It's not arbitrary. It's defined by that north-seeking test we talked about.
Yeah.
The direction of a magnetic field line is defined as the direction that a theoretical independent North Pole would move if you dropped it in the field.
Okay, so if I had a lone North Pole.
Which you can, but let's imagine. Since north repels north, it would be pushed away from the magnet's North Pole. And since north attracts south, it would be pulled towards the magnet's South Pole. So the path that follows, the flow, is north to south.
That makes sense. It's the path of least resistance for a North Pole.
Precisely.
There is one other rule about these lines that the text highlights in bold, a very important one. It says, field lines never cross.
Never. This isn't just a guideline, it's a logical necessity.
Why? What would happen if they did cross? What's the big deal?
Think about what the line represents. At any given point, it represents the one single direction of the force. It tells the compass needle, point this way. If two lines crossed, at that intersection point, you would have two different instructions.
One line saying go east, and another line at the exact same point saying go north.
Exactly. And the poor compass needle can't point in two directions at once. It's physically impossible. The resultant force at any point in space can only be in one unique direction. So if you ever draw a diagram and your magnetic field lines crisscross like a plate of spaghetti, you have broken physics.
It's like a topographic map. Elevation lines never cross because you can't be at two different heights at the exact same spot.
That's a perfect analogy. You're either at 100 meters or 200 meters. You can't be at both. A compass can only point in one direction.
Okay, so we have permanent magnets. They have a field. We know how to map it. We know the rules. But then the text introduces this scenario of the mystery of the steel pin.
Yes, this is great. This gets into the concept of induced magnetism.
The scenario is simple. You have a permanent magnet. You bring it close to a steel pin, like a sewing pin. The magnet picks it up. We've all seen that. But the text points out something more is happening. The pin itself becomes a magnet.
It does, usually a temporary one, but yes. When you bring that steel pin into the magnetic field of the permanent magnet, the pin itself transforms.
How? Is it magic?
It feels like it. But it comes back to the internal structure of the steel. Inside that steel pin, there are countless tiny regions called magnetic domains.
Domains.
You can think of them as microscopic, atomic-sized magnets, billions of them. And usually, in a normal, unmagnetized piece of steel, these domains are all jundled up. They're pointing in every random direction imaginable.
So they all cancel each other out.
Exactly. One points up, one points down, one left, one right. The net result is zero. The pin has no overall magnetic field. But when you bring the big, strong, permanent magnet nearby, its powerful magnetic field reaches into the pin, grabs those tiny domains, and twists them. It forces them all to line up.
Like a drill sergeant walking into a messy barracks and yelling, "Attention!"
That is a perfect way to put it. All the little soldier domains snap into formation and face the same way. And because they're all aligned, their tiny magnetic fields combine to make one big macroscopic field. The pin has become a magnet.
And there's a polarity rule here too, of course.
There is. Let's say you pick up the pin with the north pole of your bar magnet. The head of the pin that's touching the magnet becomes a south pole.
Because unlike poles attract, the magnet had to make an opposite pole to stick to.
It induced an opposite pole, and by extension, the pointy end of the pin, the one sticking out into the air, becomes a north pole.
So now the pin is a magnet with a north pole at its tip, which means
if you bring a second pin near the tip of the first one, it will stick to it.
you've created a chain.
You have. The first pin induces magnetism in the second pin, which induces it in the third, and so on. It's a cascade of induction. But if you take the permanent magnet away from the first pin,
The whole chain falls apart.
it all comes crashing down because the domains in the pins relax and go back to their jumbled, random state.
This leads us to a really important distinction in the text: hard versus soft magnetic materials. And we're not talking about how they feel to the touch, right? A soft iron bar would still hurt if I dropped it on my toe. Laughs. Yes, definitely. Physically, mechanically, they're both hard metals. Hard and soft in magnetism refer to how stubborn the material is about its magnetic state. It's about its magnetic memory.
Let's break down Table 16.1 from the source. It lists soft iron as a soft magnetic material.
Right. Soft iron is magnetically very easygoing. It's easy to magnetize. You bring a magnet near it, the domains align almost instantly. It's very cooperative. But, and this is the key, it also loses that magnetism just as readily.
It has a bad memory, a very short-term memory.
It forgets it's a magnet the moment the external field is gone. As soon as you take the big magnet away, the domains jumble back up. It goes back to being just a lump of metal.
And then we have hard steel.
Hard steel is the opposite. It is stubborn. The domains are kind of sticky. It is difficult to magnetize initially. You have to apply a really strong field to force those domains to turn and align. But once it is magnetized, it stays that way. It retains its magnetism.
So if I want to make a permanent magnet, like the one on my fridge or a compass needle, I need hard steel. Correct. You don't want your compass needle to stop pointing north just because it bumped into something or because you walked away from a magnetic source. You want that magnetism locked in. You need good magnetic memory.
But if I'm building an electromagnet, something I want to turn on and off, I want soft iron.
Exactly. This is a critical engineering decision. Imagine if you built a massive crane to lift cars in a scrapyard. You turn the current on, the electromagnet activates, you pick up a car.
So far, so good.
You move it over the crusher.
Yeah.
You turn the current off, and the car doesn't drop.
Because the core stayed magnetized. It became a permanent magnet.
Right. If you used hard steel for the core, it would retain its magnetism. You'd have a car dangling there, and you'd effectively have to pry it off or hit it with another magnet to demagnetize it.
That would be a terrible business model.
So you use soft iron. When you cut the power, the domains scramble instantly, the magnetism vanishes in a flash, and the car drops exactly where you want it. It's all about choosing the right material for the job.
That is a very practical application of what sounds like really abstract terminology. I love that.
Physics is usually just explaining real life, after all, once you have the language for it.
Speaking of real life, let's scale this up. Way, way up. We've talked about bar magnets and pins. Now let's talk about the biggest magnet in our immediate vicinity, the Earth itself.
Section 4. The Earth as a giant magnet.
The text describes the Earth as having a magnetic field that looks like a giant bar magnet is buried inside the planet. That's the model we're given.
It's a useful model to help us visualize the shape of the field. Obviously, there isn't a literal giant red and blue bar of metal down there with a made in the galaxy sticker on it.
Right. So what is down there? What's the core mechanism that's actually generating this field?
The Earth has a core made largely of iron and nickel. The very inner core is solid due to immense pressure, but the outer core is liquid. It's a sea of molten metal, hotter than the surface of the sun.
And it's moving. It's not just sitting there.
It is churning violently because the Earth is spinning on its axis, and because of the immense heat from the core creating convection currents, that liquid iron is spiraling and flowing in massive, complex patterns.
And iron is a metal, so it has electrons that can move freely.
Delocalized electrons, as the text specifies. These are electrons that aren't tied to any single atom. They're free to move throughout the metal. So you have a massive volume of moving charges, and as we'll learn later in the chapter, moving charges create electric currents.
And electric currents create magnetic fields.
Exactly. So the Earth is what's called a geodynamo. It is generating its own magnetic field through the movement of its molten core. It's a self-sustaining electromagnet on a planetary scale.
Now, here is where it gets really interesting, and usually really confusing for people. The North confusion.
This is the classic aha moment, or maybe the wait, what? A moment in chapter 16. It breaks everyone's brain the first time they hear it.
Okay, let's unpack this slowly so no one gets lost. I have a compass. The arrow is painted red. We call that the North Pole of the compass.
Correct. The north-seeking pole.
And it points to north, meaning geographic north, where we find Canada, the Arctic, Santa Claus.
Right. It points to the top of the map.
But using our golden rule from section 1, unlike poles attract.
Correct. North attracts south. South attracts north. That rule is absolute.
So if the North Pole of my little compass is being attracted to the top of the Earth, that means the top of the Earth must be
A magnetic South Pole.
Yeah, that is so completely counterintuitive.
It is. Geographically, we call it the North Pole. We have for centuries. But magnetically, in terms of physics, the Arctic acts as a magnetic South Pole.
So the Earth is upside down, magnetically speaking.
In a sense, yes. If you treated the Earth like that giant bar magnet model, the south end of the magnet is at the top and the north end is at the bottom, near Antarctica. That's why the north-seeking pole of your compass points up. It's seeking the south pole of the Earth's magnet.
The text mentions that medieval scientists were totally baffled by this. They thought the compass was attracted to the pole star, Polaris.
Which is a beautiful, poetic idea. Polaris is fixed in the sky. It's the North Star. So they thought there was some kind of celestial, magical attraction. But it was wrong.
Who figured it out? Who realized the force was coming from below, not above?
A man named Robert Norman, an instrument maker in London in the late 1500s, he discovered something called the dip, or magnetic inclination.
The dip.
He was building compasses, and he noticed a problem. After he magnetized the needles, they wouldn't balance properly. The north end always wanted to dip downwards. He had to add a little counterweight to the south end to make them sit level.
So he investigated why.
He did. He built a special compass that could pivot vertically, like a seesaw, not just horizontally. And he saw that in London, the north pole of the needle dips downwards, pointing steeply into the ground.
Pointing into the Earth.
Exactly. If the attraction was coming from the stars, the needle should tilt up towards the sky. But it tilted down. That was the first real proof that the attractive force was coming from inside the planet itself.
That is such a simple, elegant proof. Just look where it points.
The best experiments often are.
Now, beyond helping us navigate, this magnetic field does something absolutely massive for us. The text calls it the shield.
This is the planetary survival aspect. The sun is a life giver, but it is also a raging nuclear furnace. It is constantly shooting a stream of charged particles at us in all directions called the solar wind.
Which sounds pleasant, solar wind, but is actually incredibly dangerous radiation.
Very dangerous. It's high-energy protons and electrons traveling at hundreds of kilometers per second.
Yeah.
If that stream hit the Earth's atmosphere directly, it would strip it away over time. It would irradiate the surface. Complex life would struggle to exist.
But because these are charged particles, they interact with magnetic fields.
Right. The Earth's magnetic field acts like a deflector shield in a sci-fi movie. It extends way out into space, creating a bubble around us called the magnetosphere. When the solar wind hits this field, most of the particles are deflected. They flow around the planet like water flowing around a rock in a stream.
So we are inside a magnetic bubble.
We are. The magnetosphere. Some particles get trapped and spiral down the field lines at the poles, which is what gives us the aurora borealis and australis, the northern and southern lights. That's the shield in action.
And without that shield,
Without that magnetic field generated by the churning iron core, Earth would probably look a lot more like Mars.
what happened to Mars? Why doesn't it have one?
Mars is smaller than Earth. Its core cooled down and solidified much faster. The dynamo stopped. The magnetic field turned off. And over billions of years, the solar wind has stripped away most of its atmosphere and water. Now it's a barren, frozen desert.
That is humbling. It makes you appreciate that churning molten iron thousands of kilometers beneath our feet. But the Earth's magnetic field isn't static, is it? It changes. This leads us to Section 5, continental drift and flipping fields.
This brings in Alfred Wegener. He's a fascinating and kind of tragic figure in science history.
Figure 16.1 in the text shows his face. He's the guy who looked at a world map and said, hey, doesn't South America look like it fits perfectly into the side of Africa like a jigsaw puzzle piece?
He proposed the theory of continental drift in 1912. He suggested that all the continents were once joined together in a supercontinent he called Pangaea, and they had moved apart. But at the time, he was ridiculed. He was a meteorologist, not a geologist.
And they laughed him out of the room. Why?
He didn't have a mechanism. He couldn't explain how massive continents could plow through the solid rock of the ocean floor. Geologists said it was physically impossible, like a ship of wood trying to sail through a sea of ice.
So his idea died with him. But the proof, amazingly, came from magnetism, paleomagnetism, the magnetic memory in rocks. How does that work?
It happens at the mid-ocean ridges. These are underwater mountain ranges where tectonic plates are pulling apart. In the gap, you have volcanoes under the sea erupting magma. This magma contains tiny grains of an iron oxide mineral called magnetite.
And because they are floating in liquid rock, those grains are free to spin around.
Exactly. They act like billions of tiny microscopic compasses. While the rock is still liquid, they align themselves with the direction of the Earth's magnetic field at that moment.
And then the rock cools and hardens.
It freezes. It crystallizes into basalt. And those tiny compasses are locked in place forever. They form a permanent record, a snapshot of the direction of the Earth's magnetic field at the exact time and place the rock formed.
So if you look at the rock on the ocean floor, you have a geological tape recorder. And what did they find when they looked at this record in the 1950s and 60s?
They found stripes. And this was the smoking gun for Wegener's theory. They found that the magnetic field wasn't always pointing the way it is now.
Magnetic reversals.
Yes, the Earth's magnetic field flips. North becomes south, and south becomes north.
That sounds catastrophic. The whole planet flips upside down.
The planet doesn't flip physically. We don't turn over in space. But the magnetic field itself, the polarity, reverses. What was a magnetic south pole becomes a magnetic north pole.
And the ocean floor proves this.
Yeah. Yes. Using magnetometers, they mapped the ocean floor on either side of the mid-ocean ridges. They found a perfectly symmetrical pattern. A stripe of normal polarity, like today, right at the ridge where new rock is forming. Then next to it, on both sides, a stripe of reversed polarity. Then normal again, then reversed. It proved that the seafloor was spreading out from the middle, pushing the continents apart, and recording these magnetic flips like a giant two-way tape recorder.
Proving Wegener right decades after his death. But let's go back to the flipping. The text says this happens roughly once every 300,000 years.
On average, yes. But it's not a regular clock. It can be millions of years between reversals, or much shorter periods.
And the last one was?
About 780,000 years ago. The Brunnes-Matuyama reversal.
So we are.
We are technically overdue, statistically speaking.
We'll come back to that thought at the end of the episode, because that is a slightly terrifying thought to just leave hanging there. But first, let's move from the Earth back to the lab. We've talked about permanent magnets, now Section 6. Electromagnetism. Turning it on and off.
This is where we bridge the gap between electricity and magnetism. For a long time, centuries, scientists thought they were two completely separate forces.
But they aren't. They're two sides of the same coin.
Exactly. The Danish physicist Hans Christian Ørsted discovered this almost by accident in 1820. He was giving a lecture and noticed that when he switched on an electric current in a wire, a nearby compass needle twitched. Electricity creates magnetism.
The text introduces the solenoid, which is just a fancy word for a coil of wire.
Right. If you take a copper wire and wrap it around a pencil or a tube to make a spring shape, that is a solenoid.
So how does it work? Why is a coil better than a straight wire?
And a straight wire carrying a current has a magnetic field, but it's weak, and it's in circular loops around the wire. Not very useful. But if you coil that wire up...
You overlap all those little fields.
Exactly. You concentrate that field and you shape it. The magnetic field around a solenoid, a coil of wire carrying current, looks almost identical to the field around a bar magnet.
It has a north pole and a south pole.
It does. Figure 16.11 in the text shows this clearly. The field lines come out of one end, loop around the outside, and go into the other end.
How do you know which end is which? If it's just a coil of wire, it looks the same from both ends.
There's a rule for that. You can look down the tunnel of the coil from one end.
Okay, picturing looking down the tube.
If the conventional current is flowing around the circle in an anti-clockwise direction, that end is a north pole.
And if it's flowing clockwise?
It's a south pole. There are other tricks, like the right-hand grip rule, but that's the simplest way to visualize it.
Okay, that's a handy trick. But the biggest advantage here, as we touched on with the scrapyard crane, is control.
Total control. A permanent magnet is always on. You can't turn it off. An electromagnet is a magnet on demand. You control it with a simple switch.
We mentioned the scrapyard crane in figure 16.12. Current on, lift the scrap. Current off, drop the scrap. But the text also mentions things like electric bells, relays, and motors.
All of those rely on this exact principle. A relay is a particularly clever application.
How does a relay work? What's it for?
Imagine you want to start a car engine. The starter motor requires a huge amount of electrical current, hundreds of amps, enough to melt a small switch or give you a very nasty shock if you touched it.
So I don't want that huge current running through the ignition key in my hand.
Exactly. So you use a relay. When you turn the key, a tiny safe current, maybe less than 1 amp, flows from the dashboard to a small electromagnet under the hood.
The magnet turns on?
That small magnet pulls a heavy metal lever across a small gap. That lever closes a different switch, a heavy-duty switch that can handle hundreds of amps. And that switch connects the battery to the starter motor.
So the small, safe current controls the big, dangerous current using magnetism as the bridge.
Precisely. It keeps the user completely isolated and safe from the high-power circuit. It's ingenious.
Now, if I'm building an electromagnet, I want it to be as strong as possible. I don't want a weak magnet that can't even lift a paperclip. Section 7 covers the variables affecting strength, and it uses a specific experiment, Arun's investigation.
Activity 16.3. This is a classic classroom experiment set up to measure magnetic strength.
Let's visualize it. Arun has an electromagnet, a coil of wire wrapped around an iron core, and it's clamped in a stand, pointing downwards.
And underneath it, on the table, is a top pan balance. Basically, a sensitive digital kitchen scale.
And on the scale, he places a permanent magnet.
Now, here's the clever twist. He sets it up so the poles are the same. A north pole facing a north pole, for example, so the magnets repel.
Why repel? Why not just see how much it can lift through attraction?
You could, but it's tricky to measure. If they attract, the electromagnet pulls the permanent magnet up, the reading on the scale goes down, it might even go negative. It's hard to get a precise reading of how much pull there is.
But if they repel?
The electromagnet pushes the permanent magnet down, it presses it into the scale, the reading on the scale increases.
It adds weight.
Effectively, yes. That increase in the reading is a direct measure of the magnetic force pushing down. It's much easier to measure accurately.
So Arun changes the number of turns in his coil and measures the reading. Let's look at the data in table 16.3.
He starts with just 6 turns of wire. The reading on the balance increases by 0.21 grams.
Then he goes up to 20 turns.
And the reading jumps to 0.59 grams. A much stronger push.
So the trend is clear. It's not a surprise, but it's good to see the data.
More turns equals more strength. The magnetic field is stronger, so the repulsive force is stronger, so the scale reading is higher. It seems to be a roughly linear relationship.
The text summarizes 3 ways to increase the strength of an electromagnet. 1. Increase the number of turns in the coil, as Arun did.
2. Increase the current. Pump more electricity through the wire. More moving charge per second means a stronger field.
And 3. The one we already discussed a bit.
Add a soft iron core.
We're back to soft iron again.
Yes. If you just have a coil of wire with air inside an air core solenoid, it works, but it's pretty weak. Air isn't a great conductor of magnetic field lines. The lines spread out.
But if you shove a rod of soft iron inside that coil,
the soft iron becomes strongly magnetized, and it concentrates the magnetic field lines. It acts like a lens for magnetism. It makes the magnet significantly stronger, hundreds or even thousands of times stronger than the air core alone.
So for a supermagnet, you want lots and lots of turns, as much current as the wire can handle without melting, and a big soft iron core right in the middle.
That's the recipe.
So we've covered the basics, the earth, and how to build our own magnets. Section 8 is about looking ahead, connecting this chapter to what comes next.
Right. Chapter 16 is really a foundation stone for some much bigger ideas in physics.
The text explicitly mentions that this sets the stage for Chapter 20, electromagnetic forces, and Chapter 21, electromagnetic induction.
Because once you understand that electricity creates magnetism, which is what we just did, the next logical question is, can you do it the other way around?
Can magnetism create electricity?
And the answer is yes. This is what Michael Faraday discovered. If you move a wire through a magnetic field or move a magnet near a wire, you generate a current, you induce a voltage.
And that is the basis of, well, modern power generation.
It's the basis of every single power plant in the world. From nuclear and coal plants that use steam, to spin turbines, to wind turbines, to hydroelectric dams. They're all just different ways of spinning magnets inside coils of wire, or spinning coils of wire inside magnets to generate electricity.
And motors are just the reverse, using electricity and magnetism to create movement.
The link between electricity and magnetism, this whole field of electromagnetism, is arguably the most important scientific discovery for modern civilization. Without it, we don't have the grid, we don't have electric appliances, we don't have electric vehicles. We are back to steam power and candles.
It's the invisible backbone of the entire modern world.
It really is.
So let's wrap this up. We've journeyed from the simple red and blue bar magnet to the churning, molten core of the Earth.
We've seen how invisible field lines can be mapped with iron filings and clotting compasses. We've learned that the Earth protects us with its magnetic shield, the magnetosphere.
We've seen how magnetic stripes on the ocean floor were the smoking gun that proved that continents actually move.
And we've learned how to harness this force using coils of wire and soft iron cores to build the machines that run our industries. from scrapyard cranes to the relays in our cars.
The key takeaway for me is that magnetism isn't just a force we use for convenience. It's a force that allows us to exist. It protects our atmosphere. It gives us a way to navigate. It powers our world.
And it's dynamic. It's not a fixed, dead thing like gravity seems to be. The Earth's field is alive, and it's constantly changing.
Which brings me back to that provocative thought we pinned earlier, the magnetic reversal.
The one we are overdue for.
The text and other sources say the field decreases significantly before it increases again in the opposite direction during a reversal.
That is the major concern. During the transition, which could take hundreds or even thousands of years, the Earth's shield gets weak. Very weak. Maybe only 10% of its current strength. And it becomes more complex, with multiple north and south poles popping up all over the planet.
And we know that some scientists speculate that species might have gone extinct during previous reversals because of increased cosmic radiation reaching the surface. But those species didn't have satellites. They didn't have GPS. They didn't have global power grids.
Exactly. Even if a reversal doesn't wipe out humanity biologically, we'd likely survive, maybe with higher rates of skin cancer. Think about our technology. Our entire civilization is an electronic house of cards. A weakened magnetic field lets in more solar radiation. Those charged particles fry sensitive electronics.
So a magnetic reversal today?
Could be a technological apocalypse. No GPS means global shipping and aviation halts. No satellite communications means global banking and the internet fail. Massive electrical currents induced in our long power lines by solar storms could melt the grid, causing blackouts on a continental scale. We are far, far more vulnerable to the Earth's magnetic whims than any other species has ever been.
On that cheery note, but really, it makes you appreciate the invisible force field we have right now, protecting us.
Absolutely.
Yeah.
The next time you see a compass needle point north, just remember the chaotic, churning ball of molten iron deep below your feet that's making it all possible.
Thanks for listening to The Deep Dive. Go check out Chapter 16 again with fresh eyes. We'll see you next time.